Okay. Okay, this is our group, Mark and Mark right now for chapter 5. We're studying for we're gonna do 5.1 and 5.2, okay, of the ARRL manual. Gonna go over it and explain it, and so that you guys could see how easy it is. And 5.1 is going to be on basic modes and bandwidth. And here I'm just going to jump to 5.2 real fast on the screen. Radio's building blocks. So this is really going to be fun tonight. And we're going to just go through this page by page on the screen and talk about it. Okay, so we're starting with the basic modes and bandwidth. What is a mode? Okay, and the combination of modular, and I'm going to just okay, let's go through everything just so that we're kind of comprehensive.
Okay.
Okay, the first question: what name of the process that changes the phase angle of an RF signal to convey information? Now, what that is that's phase modulation, or PM. Okay, and so just so you guys know, the general class license manual and the test just gives you basic 1 or 2, or at the most half a page explanation for everything. To really go deep and to understand this, okay, you can be, taking college courses in it. So we're just going through the basic 1 or 2 line definitions of these things so that the people watching this can have help to take their general class license. So the name and process that changes the phase angle, and I'm not going to explain phase angle of an RF signal, is phase modulation. And what is the process that changes the instantaneous frequency of an RF wave to convey information? That is, I believe, modulation. And what type of modulation varies is instantaneous power level. That is the power level and that's amplitude modulation. Okay, so you're going to have a handful of basic modes, privileges as a general class. You're going to have continuous wave, which it doesn't modulate at all. It just sends out the carrier of whatever that frequency is, and it is a sine wave. So on a scope, it'll show it's a sine wave, but it is just and it's not going to modulate. That sine wave will be converted in your receiver, and you'll hear a tone, but it's just on and off and on and off, and that's how the continuous wave is modulated in that sense. It's just on and off. That's called CW. That's using Morse code. Then you have CW, and then you have AM, which takes the instantaneous power level. Oh, I know what's saying. The instantaneous frequency on this third one, Mark, that's FM. FM.
I was thinking FM because we got the AM. I mean,
it is FM. Yeah, that is correct. Since I'm talking with you now, it's coming back to me. So that's FM, the instantaneous frequency. So with FM, you're varying the frequency, and there's a little chart here. You'll see the bandwidth, okay, of all these things. And which of the phone emissions uses the narrowest bandwidth? That's continuous wave. So we're going to hit here really briefly on the basic modes. And we're going to, the basic modes we're going to touch, they're going to also mention digital mode in here, okay, which is only uses a computer. And actually, RIDI is a digital mode, pre-computer. I don't know if they mention it in this chapter, but we're going to have CW, we're going to have AM, we're going to have single sideband, which is which is the same as AM, but it strips it strips half of the sine wave off. It strips half of the bandwidth. Okay, so if you have, and they talk about double sideband. So if you look at a sine wave and you see the above the line, that's upper, and below the line, that's lower. And if you strip out the carrier, that's called double sideband. And there's various ways of stripping out the carrier frequency, which would be used for CW, and you strip out either the upper or the lower sideband. And what you're doing is you're putting all your power into that narrower, okay, narrower bandwidth, and that was developed by Art Collins of Collins Radio, and that is what goes far further. Now the full sine wave is AM, and it'll sound better. With single sideband, you can make it, you could tune it in really well. You have to tune it in within that frequent bandwidth parameter, and you can get rid of the Donald Duck talk. But it's more forgiving with AM because it's a much larger bandwidth, and you hear the full voice. Okay, so anything you want to share with that, Mark, before we go to the next page?
Well, I think isn't that where you trade off the power for the quality of audio?
Yes.
Yeah.
So FM gives you the best quality audio, like we've learned. Okay, kids growing up, okay, in the U.S. and when FM radio came along, boy, there was no static at all, like Steely Dan said. Okay, and so the best quality was FM, and so we will get into that eventually. Okay, next page here. Amplitude. Go ahead, Marcus.
Remember AM radio in the car, whenever you went under underpass or something, you would lose the station.
You would.
So there's I never really understood that way back when, why you would lose that the music very briefly like that. But that was part of, I think, the big push with the FM, is that you didn't get that loss of signal because of something in the way. It was like a wider signal.
Yes, a much wider signal. And so here's the little paragraph on this. And varying the power of the signal is called amplitude modulation, or AM. Everybody's familiar with AM radio. And the information is contained in the signal's envelope or bandwidth, and that includes the maximum. The envelope is more than the bandwidth. The bandwidth is the frequency spread, and the envelope is the bandwidth, including the height and the power levels. Okay, and and the way, and it says the process. Let me get you out of here real quick. So there, I just had you. The process of recovering speech or music from the envelope of an AM signal is called detection. And that AM signal is a carrier and two sidebands. Okay. The AM signal's carrier is a continuous wave. And the amplitude does not change and carries no information. Okay. So an AM signal modulated by, so I guess I could be wrong on that in my earlier statement saying that it's a sine wave. It's not, it's just a continuous wave, but it's a continuous wave, still a wave. Okay, so it'll look on the oscilloscope as just a straight line, but it is a wave, even though it doesn't show that way on the scope. An AM signal is modulated. What that means is you are adding the information in this situation with us. It's voice, okay, and we're not, because we don't play music over ham radio. So the AM signal is provided the voice, your voice, and the upper sideband is higher in frequency than the carrier tone, and the lower sideband is lower frequency. And so the AM signal with carrier on one sideband is called single sideband, or SSB. And that is, and it says here, the wider AM signals have a fuller frequency response that sounds warmer on the air. So I had kind of gone over that. Then we go into frequency and phase modulated modes. Okay, so frequency modulation, FM, we're familiar with. And PM is phase modulation, and it has to do with the signal's phase angle. And they're both types of angle modulation. They have constant power, and they use the same kind of electronics. So the same circuitry will work for FM and PM. PM is just another type of FM. And down here, a bandwidth definition. Composite signals are a group of signals to create a complex signal. Okay, so, and here we have, and I guess, you know, our FM and PM and AM and SSB are composite signals. And because it says they have components, they cover a range of frequencies, and that that's called bandwidth. So let's see what the next page looks like here. Here, okay, we show the bandwidth. Okay, we show 26 dBs is the signal power that they allow. The FCC defines bandwidth as the width of the frequency band in which the mean average power is attenuated to 26 dB below the mean power. Okay, and that's all they tell you about this. Okay,
So that's really just where all those spurs kick in. That bandwidth, they kind of say, okay, these noise signals are too low to be counted. That's what that minus 20 or the 26 dB.
It has to do with the noise.
Yeah, see you see all those spurious emissions on both sides of what they're calling the bandwidth.
Okay.
That's noise of some sort, but it's not high enough in amplitude to / power, amplitude in this, the way it's drawn out here, to cause some kind of interference in what your bandwidth is.
Okay, gotcha. It's not interfering with beyond that bandwidth. And we'll go into the bandwidth at the next page. And so let's go here. Okay, here is amateur signal bandwidth. Okay, so here we have the bandwidth Mark was talking about here. Down, the smallest bandwidth is CW, which is your Morse code. And it's 100 to 300 hertz. Okay, that's really, really small. And then your AM voice is 6,000 hertz, 6 kilohertz. And your SSB voice is 2 to 3 kilohertz. Why? Because it removes an entire part of the signal, either the upper or the lower. And so SSB voice is 2 to 3 kilohertz. So it's half or less than the AM voice, including the stripping out of the carrier. And amateur television is huge, 6 megahertz. That takes a lot. Okay. And here we have digital modes can go up to 3 megahertz. Okay, 50 to 3,000 hertz. Oh, 3,000 hertz is 3 kilohertz. So no, not that's 3 kilohertz, not megahertz. So that's digital mode. And FM is 5 to 16 kilohertz. So a radio signal at one frequency whose strength never changes is called a continuous wave, CW. Adding information whether it's changing its frequency, phase angle, or amplitude, is called modulating it. Recovering the information from a modulated signal is called demodulation. And by the way, phone, which we call voice, is short for radio telephone signal. That was the original term back in the 20s, because it was all people had was telephones back then. And so they were using radio, they were using telephone, using radio. So it's called radio telephone. And then if data, it modulates a signal, it's data mode, and it has to be a computer. That are digital and data modes are the same. Let's see if we missed a page here, because I kind of like jumped. Nope.
No, you didn't.
Okay, next page. Okay, so the instantaneous, the term instantaneous, whether it's amplitude, frequency, or phase, is the value at a specific instant of time. So folks, this is just baby stuff. It's so easy, and you can see how easy it is. So now we're going to get a little harder. We're going to go into radio's building blocks. I don't know if, I think I finished studying this. Okay. And it's really not hard either. Okay, so let's go through some of these up here. Which of the following are basic components of a sine wave oscillator? Okay, we'll find out. What determines the frequency of an Lc oscillator? Now, here we hit Lc oscillator. Now, we're going to go and explain oscillators in a minute, because we're going to talk about the basic building blocks of radio. And I think I didn't go past transmitters. I don't think I got into the receivers, and that's where we're going to stop. But what determines the frequency of an LC? L is the symbol for is the symbol in electronics for coil, and C is for capacitor. So LC oscillators are tunable oscillators using a coil and a capacitor, both variable coil and variable capacitor. Which of the following is advantage of a direct digital synthesizer? That's how radios are today. Okay, and we're going to get into that. And then they want you to know, what is the phase difference between the I and Q signals that software-defined radio SDR equipment uses for modulation and demodulation? What is the advantage of using I and Q signals in software-defined radios? Okay. And what is meant by a software-defined radio? Software-defined radio is the big thing. Everything's going to be software-defined someday. And what is the frequency above which a low-pass filter's output is less than half the input power? Okay, we'll cover that. And what term specifies a filter's maximum ability to reject signals outside its pass band? What term specifies a filter's maximum ability? Okay, we'll hit that. Bandwidth of a bandpass filter is measured between its upper and its lower. Okay, a bandpass filter is a filter that cuts off unwanted frequencies above and below, and it only allows the frequencies within those two parameters to pass. That's why it's called bandpass. And what term specifies the filter's attenuation inside its pass band? Insertion loss. That's called insertion loss. Which of the following is typical of a direct digital synthesizer? Well, we'll have to see. And what emission is produced by the reactance modulator connected to a transmitter RF? Any questions on that, Mark?
Nope, not yet.
Okay, let's see what we get next. Amplifier stage. That's it. What is another term for mixing the two RF signals? Well, we're going to have to hit all this. At what stage a VHF FM transmitter generates a harmonic of a lower frequency to reach at what stage in a transmitter It generates a harmonic of a lower frequency to reach the desiring operating frequency. And what is the combination of mixers, local oscillator, and RF input is found in the output? Okay, well, we'll have to learn. Okay, so nearly all radios are made up of just 4 different types of circuits. And they're going to cover they are oscillators, mixers, multipliers, and modulators. So we're going to find out what this is about. These functions can be performed with the new technology, which is digital signal processing, DSP, which is also referred to as software-defined radios. Even though non-software-defined radios can have digital signal processing within it, they've had since maybe the 80s. Filters are used to attend, and I know that the Collins radio, the Collins main, I believe is KMW, their last ham radio that they came out in like 1980 something, was like 1982, was like $4,500 back then, and it used DSP, digital signal processing. Filters are used to attenuate, to reduce or pass signals in a defined range. Filters are classified there by the response and the pass band. Also, attenuation could be called rejection, or the attenuated signal can be called stop band. And here's some pictures, and I'm going to skip that. You'll have to look in your own book because I can't make them bigger. Low pass filter is one that cuts off all frequencies below the cutoff frequency. Actually, all frequency below the cutoff frequency are passed with no attenuation. And a high pass filter is all signals above the cutoff frequency are passed, and the ones below it are attenuated or ended. Okay, or severely attenuated. And a bandpass filter has both an upper and lower cutoff frequency, and signals between the cutoff frequency are passed, and those outside the pass band, or the upper and the lower, are cut off. And the opposite of a bandpass is a band stop filter. It's like a notch filter. It only attenuates. It's the reverse of the bandpass filter. Between the upper and lower cutoff frequencies is what is cut out. And so it's stopped. And it's also called a notch filter. And even though a filter can pass a range of frequencies, it may still attenuate channels in its pass band. That's called insertion loss. Oscillators. The function of most oscillators in radio is to produce a pure sine wave. Okay, back to we were talking in the last section 5.1. I was saying that it was even CW is pure sine wave, because the wave is, it is a radio wave. I mean, I think we don't see the pure sine wave on an oscilloscope, but I haven't used an oscilloscope, so I can't tell you. I've watched them, and that's about it. So the function of the oscillators. What'd you say, Mark?
I'm pretty sure you get the actual sine wave on an oscilloscope. That's kind of the thing with the oscilloscopes, is you actually see the true peak to peak.
Right, but for a continuous wave, I'm not sure. I mean, it could be displayed just as a line. I don't know, Mark.
Well, it depends on how close you zoom in, because there's always going to be some kind of a modulation happening.
Yeah, okay. Well, that's something to play around with. And I want to tell you, there are some unbelievable cheap brand new oscilloscopes you can get from that are out there now. I mean, you're talking under $400. You can get a fantastic, they're on the IEWR website advertised, where you can get these oscilloscopes. And I'm thinking of it. I don't know which one to get, so I'm waiting,
Yeah,
until I need one. So, okay, let's take a look at the next page here. Okay, here's the block diagram of an oscillator circuit. it says oscillator. It has the circle with a sine wave. You have an amplifier, and you have this box, which is the feedback. So the amplifier produces gain, and it feedbacks, it sends some of that back into this feedback circuit. It goes back in there. And so what this does, they explain here. An oscillator consists of an amplifier, the triangle, that increases the signal amplitude or gain, and a feedback circuit, the rectangle here, that routes some of that output signal. Here's the output signal over here. Okay, back into the amplifier. And as long as it's greater than 1, the circuit's output is called oscillation. It's self-sustaining. And that's what it's meant to do. Okay. And to make an oscillator to produce a signal frequency output, the feedback circuit must include a filter. Okay, so that the filter will be like a notch filter. It'll only pass whatever the frequency it's designed for. And there are 2 basic fixed frequency oscillators. There's the LC. Okay, LCs are also which is coil and capacitor, and it says that here. The LC oscillators is an inductor, L, coil, and capacitor, and crystal oscillators. So you see crystals in the older, all the older equipment. Now, when you have an LC circuit, it stores electrical energy like a flywheel. And the resonant frequency of the LC circuit is the frequency of the oscillator. So that's how it's an artificial oscillator rather than it's an electronic oscillator rather than a crystal oscillator. So a quartz crystal is often substituted for a LC tank circuit. It's crystal oscillator. And it's orders of magnitude. A magnitude is 10 to the first, which is 10, or 10 to the second, which is 100. More orders of magnitude, more precise than these LC circuits. So that's why they're used as stable signal sources for different bands in radios. Like if you have a old Yaesu transmitter, it'll have oscillators for all the bands, and yours might not have them, and you have to buy them and put them in. Same with the receivers. It'll have oscillator crystals. But it'll also have a variable frequency oscillator. The crystal oscillator is just to focus it on that band, and then the variable frequency oscillator takes over. It tunes the radio to different frequencies on where that crystal oscillator is working in that circuit. And the other types of circuits are phase lock loop, PLL, which when I was a kid, I thought that was the coolest term, phase lock loop.
Yeah.
Did you too, Mark?
Yeah.
I thought, man, that is the coolest thing. I had no idea what it was, but I thought it was cool.
Yeah.
And direct digital synthesizer, that came out, I think, starting with the Collins in the 80s. And other people picked up on it right away. And that's what the software-defined radios all have today. All the modern radios use direct digital synthesizer. And it says the DDS has the advantage of being controllable by software and has stability comparable to a crystal oscillators. But I want to tell you, there is noise in a DDS software-defined radio. There is noise, I forgot, because I read a book on software-defined radios that cannot be removed. Okay, sort of like when you have people that say that records have better fidelity than any kind of digital mode for music, they're absolutely right. Because the record is the full analog, the exact duplication of the music or the voice. and all these compact discs or DVDs or whatever, they all use sampling algorithms and they miss. And these sampling algorithms produce noise that cannot be removed. So there is an advantage to the old way as well. Okay, so the next thing we have is mixers, a key function to both receivers and transmitters. And I'm going to stop at the end of the transmitter here, and we'll pick up next week. But a key function to both receivers and transmitters is the ability to change the frequency of a signal. That is called mixing. And let's go here. Oop. Okay, here is a mixer. It's got the little circle with the X. You have the local oscillator, you have the RF input, and then you have the output. How does it do it? Okay. Okay, there it is. There's the picture. Next page. Okay, the process is called heterodyning. Okay, hetero, like heterosexual, is different. Means the Greek word for different. So man is different than a woman. Okay, man will always be a man, woman will always be a woman. There's no such thing as it being both the same. It does, and that goes down to the DNA and the actual, what do you call it? The chromosomes. Okay, you can't ever make a man a
Right.
woman.
We're not going to worry about being politically correct on this thing. We're going to.
Yeah, you cannot make a man a woman and a woman a man. So that's where the old Greek word comes, is hetero dining. And the dining, I can't tell you what that is, but the hetero means different. So you're taking two different frequencies, you're mixing them, combining them. And whenever you mix frequencies, you get upper and lower frequencies. And this is how mixers can change signals to any other frequencies. And that's all you got to know how it works. It doesn't get into it for the general. But when you get more into radio and you want to start fixing them, you have to learn how they work. So the F1 is referred to as the RF input. F2 is the local oscillator, and the mixer outputs are mixing products. So the next building block of radio is called multipliers. Oh, and the big thing you have to learn this, that what a modern mixer is called heterodyning. That's how they produce the different signals. Okay, and this goes back to the 1920s, I believe. Okay, so they had to find out, how in the world am I going to be able to tune in, okay, all of these different signals. Before heterodyning, you had to have crystals for the specific so if there was a radio station, like in Chicago, was WLS, was the first radio station, I believe, in Chicago, and it stood for Sears, world's largest store, which was destroyed by a psychopathic, evil person that dismantled it for his own greed. And just the greatest some of the evils of capitalism, okay, that destroyed that company, Sears, for his own greed. Okay, so we know where people like that will go. Multipliers. So a circuit that acts similarly to a mixer is called a multiplier. Instead of creating sum and difference of two input frequency, it uses the harmonic. So multipliers are used for stable VHF and UHF. Okay, heterodyning mixers are used for HF rigs, which is the general, which is your shortwave, which are much lower frequencies than very high frequencies and ultra high frequencies. You can't heterodyne those. You have to use the multiplier, and it uses the multiplier. Makes harmonics. Mark mentioned harmonics earlier. It makes wanted harmonics. Okay, and so that's the building block for the higher frequencies. Here's a picture. And modulators. Okay, the final thing, other than we're going to get in, probably going to talk about amplifier circuit. but modulators are the circuits that add information to the carrier signal. Realize that a pure carrier is continuous wave, whether at a specific frequency. It's just that wave, because we're talking, the frequencies are radio waves. Okay, so it will show that sine wave that Mark and I talked about. And so to add information, and voice is information, okay, you have to modulate it. And we talked about this at the beginning. We talked about the amplitude modulation. That's the first type of modulation other than Morse code over radio, which was the first thing, was Morse code. And then we added voice, and voice came about by varying the power, okay, of the power of the supplied to a tube, okay, to on a transmitter, and by varying the power, it varied the amp modulation, and somehow the voice is added to that. So it doesn't go into how it's added to it, but deeper study will give you that information. And then if the carrier, and so here it talks about the upper lowered sideband that we discussed earlier. Let's see what we got next, Mark. We got pictures here. Okay, we don't need that. Then we're going to this again. Here, frequency and phase modulation. We talked about that. So change in signal frequency is deviation. That's interesting. Okay. And that's part of this phase modulation thing. And the common method performing phase angle modulation is reactance modulator. Okay, so if you want to understand this, you're going to have to come back on your own and read it, because we're just zooming through. Now, quadrature modulation, this is new stuff. This happened only in the last 10 or 20 years for software-defined radio. And, you know, if you want to get a good book on it, the ARRL has a couple books. One of them is SDR, Software Defined Radio. And that was this great book. It explains all this stuff. First edition 2016. It's new. All this stuff is new. Really new. How new it is. I think they've been playing around with it 10, 20 years, but in ham, it's pretty new. Quadrature modulation is called the Iq modulation because you have I and Q signals that create the modulated output. And the I and Q signals can be made through software to produce any form of modulation. It's all done through software. I refers to in phase and Q to quadrature. So the RF carrier from the local oscillator on a transmitter is split into two signals. One which phase shifted by 90 degrees. That's where the quadrature comes from. And then they are combined and modulated together. And this is all you have to know, basically, is this page. Okay, and to study it up for the you got to be aware of it. And 5.3 is transmitters. Okay, so we finished 5.1 and 5.2. That was my goal. And let me stop the screen share. Go back to Mr. Mark. Okay, Mr. Mark, we did it. We did 5.1 and 5.2. And so at least we'll venture into 5.3, maybe 5.4 for the next session.
Okay.
Thanks for showing up, for helping, and for helping.
Stop the record. Hey.
Oh, I got to stop the record. Hold on. Hold on. Record.